Welcome to this video. In this lecture, we're going to talk about classification and more specifically classification trees in more details. We use classification trees to motivate the topic of machine learning, and one of the classical examples of classification trees is to basically uncover some of the decision processes that are used in organizations just by looking at data. Now, these decision trees are deployed commonly to provide guidelines for people making decisions on how they can make these decisions. And these trees are usually created by experts, domain experts, who based on experience can come up and create these guidelines. This decision tree that you see here is one such decision tree for approving or not approving loan applicants for loans. This decision tree makes some choices based on the values of some of the variables, and at the end, the decision is going to be loan or no loan. These variables are basically the features in the data itself, and the final outcome is basically the outcome variable or the outcome array. So we're going to look at decision trees, and we're going to use decision trees on a couple of the data sets, and we're going to introduce some more concepts about machine learning, including training and testing and overfitting. Let's first revisit the IRIS dataset. Now, this IRIS dataset, which also comes preloaded in scikit-learn, but we have it here anyhow, contains 4 features: sepal length, sepal width, petal length, and petal width, as well as one outcome array, which is species. We're going to create a decision tree classifier, and it's very similar to creating a linear regression. Again, one of the advantages of using scikit-learn is that it has a clean and easy-to-use API. So first, we have the feature matrix and the outcome variable. Second, we create the machine learning model, which is a decision tree classifier. Now again, it's a classifier because the outcome variable is categorical, right? We have 3 species. We don't have a continuous variable here, just 3 species. Hence, we want to use a classification model such as decision tree. Next, we're going to fit the model to the data here by calling the function fit. Next, we're going to fit to predict x to get y fit, right? This is the predicted values compared to the real values, which are the y. Now here, very similar to the linear regression, we can test how our model is doing by comparing y to y fit. The difference here is that y and y fit are not numerical, they are categorical here. So doing something like minus here doesn't make sense because those are not numbers. What we can do, we can compare them. You can compare whether y is equal to y fit, and then we can take, because that comparison will either give you true or false, and true will be considered to be 1, false to be 0. We can take the sum of that, and we can divide it over the length of that outcome array, and that tells us the percentage of times the algorithm makes the correct prediction, which is 100% in this case. Indeed, this number, which is called the accuracy score, there is a function, built-in function in scikit-learn called accuracy score that gives us the same. So if we import accuracy score, we can calculate the accuracy score of y fit to y. And in this case, it's the same, it's 100%. Another useful function that we can use is called confusion matrix. Confusion matrix basically shows us a more kind of fine-grained representation of where the algorithm, the machine learning model, is making mistakes. So here, for instance, you can see the correct class on the x-axis, and on the y-axis you can see the predicted one. Of course, this particular machine learning model, this particular tree, is not making any mistake. Hence, all of the values here are on the diagonal, and we have zeros here. It's not making any mistake at all, which is good news, right? So at the end of the day, we gained 100% accuracy score. Is this something good? Well, it really depends on the application of this algorithm, and there are 2 things we need to keep in mind. Well, first, are we using this algorithm to explain the underlying pattern, to understand the underlying patterns of the data. The second one, or are we using this algorithm to predict data that we haven't seen? Meaning, let's say we have new flowers that we're making a measurement on, and we want to predict their species. That's one criteria, and this is called using for explanation versus using for prediction. The second criteria is basically when we take a look at this model, how complicated the model is, and whether we have any preference toward complicated versus more parsimonious models. And those two criteria are kind of dependent. Let's take a look at our decision tree here. I'm going to print it using the function export text. And you can see that this decision tree has probably 4 to 5 levels, right? It's making decisions based on the petal width first, which makes sense because that's the most discriminating variables, as we have seen last time when we looked at the scatter plots. And then it's looking at other variables to make its decision. Kind of as a segue here, this is not it's kind of related but not really needed here. We can plot the decision tree by exporting the decision tree to a format called GraphViz, and we can either have a package called PyGraphViz to visualize it in Python, or if we don't want to install the package, we can use like any website such as WebGraphViz to visualize the package here. So what we can do then, we can copy this text here and paste it to this online tool called WebGraphViz. Then if we click on Generate Graph, it's going to create a decision tree for us. It's much more useful than the text printout. And again, this can be created within the notebook, but you need to install a package called PyGraphViz. But it's basically the same idea here. We only have 4 features of interest, and this tree is doing way more than what is desirable for such an easy task, because it's examining these, the same variables multiple times, like petal width once, twice, and then petal length, and then petal width, and then sepal length, right? Or sepal width, petal length again. Ideally, for instance, if I want to communicate this process, let's say, to a research assistant, I don't want the research assistant to look at petal width like 3 times. Take a look at petal width. If it's less than this value, take a look at the other variable. If it's, but less than this value, then take a look at the other variable. And this one is re-examining the variable multiple times. So my assessment here is that for such a simple task, this decision tree is doing too much. The model is not very parsimonious. Now, as for the accuracy score itself, this is kind of related to the model complexity, because this model is fitting the data exactly, and this is called in the machine learning terminology overfitting. Many often we don't want the model to fit the data exactly as is, because we want the model to be robust enough to accommodate data that we don't see. What I'm going to do now, instead of training the model on the whole data set, I'm going to train the model on a subset of the data. This is a very important concept in machine learning, because we don't want the model to overfit the training data. We want the model to be good enough to be able to predict unseen data. So we usually split our data to 2 data sets, a data used for training and a data used for testing. I imported a function called train-test-split, and this function takes the original data, the x and y. It can also take optional parameters, such as whether you want your data to be split randomly. I provided a seed for my random number, so the results remain the same, but you can change that. And also the percentage of data you want to put in your training versus your testing. In this case, I did 50% each. The remaining process is the same. So what I'm doing now, I'm just fitting the model. And then once I fit the model, I don't predict the labels for the X train. I create the labels for the X test. This is an important step. So I'm going to first put these in another cell, and I'm going to do yFit train is equal to decision tree predict X train. Okay, and then I'm going to do the accuracy score of my Y train and yFit train. And you can see that it's 100%. This is not surprising because the machine learning used this data to train, to optimize its parameters. So evaluating the machine learning on the same data that it has seen is not very useful if we are seeking to use the model for prediction, if you want to predict values that the machine learning model did not see. What makes sense here is to use the model that we trained on X train, Y train to predict values that it hasn't seen, the X test and the Y test in this case. If we do this, you can see that the model is no longer doing 100%, it's 96%. Again, that's not bad, but it's not 100%. And if we plot the confusion matrix here, you can see that the model is making mistakes, is mixing the second category with the third one, which is, forget the names of the categories, and the second and the third one with the second one. And that's actually kind of complies with our understanding of the data. The first category, the setosa, is very easy to discriminate, to differentiate between the other two ones, but there is a confusion in the two remaining categories. If I plot the tree here, you can see it's much more compact here than the original tree, which is actually good because this is a more parsimonious model. It's easier to understand, it's easier to use to explain the underlying data, and it's also easier to communicate. This takes us to the topic of using a machine learning model for prediction versus using it for explanation. If we want to use a machine learning model for explanation, then we usually strive for simple models because we want the model to be parsimonious so that we can, as human users, designers, look at it and understand it. If we want to use a model for prediction, then the parsimony of the model is not very important. The model can be as complex as it needs to, as long as it makes good predictions. This is probably well illustrated in more kind of recent advances in machine learning. Models such as deep neural network are so complex to be able to look at it and understand it, and many often they're called black boxes. But those models work well for a large range of complex tasks. If we want to predict, for instance, we want to do face detection, we want to predict the identity of a person given its face. The model itself is very complicated, but we really don't care about what it does, as long as it's doing a good job in prediction. Now, unfortunately, this is no longer the case because there are so many concerns about things like transparency and fairness of machine learning models, or whether these models are reflecting some underlying biases against, when these models are deployed in a socio-technical context, such as the example of using face recognition, for instance. So that issue of prediction versus explanation has ramifications beyond using the model for prediction or using it for explanations. What I want to talk about here, I want to talk about tuning the model for prediction versus explanation by providing some hyperparameters. So what I'm doing here now, I'm going back to my decision tree and I'm saying, well, I want the model to be more parsimonious because I want to use it for explanation. So I'm providing here an extra hyperparameter, which is the max depth of the tree. I don't want my tree to be very deep. I want it to be more shallow because I want it to be more parsimonious. So that's what I have done here. And notice that my accuracy score got reduced from 96% to 89%. So that's a reduction of 7 percentage points. But on the other hand, if you take a look at my tree is much more kind of parsimonious now. It only has a depth of 2, and it's only actually looking at 2 variables, petal width and petal length. We can actually export the tree to GraphViz format and visualize it. So be more appealing visualization than the text output. But you can see such a condensed tree is much more useful for understanding what's going on. If I am to explain this to my research assistant now, I can tell the research assistant, well, there are only two variables you need to look at, petal width and petal length. You first take a look at petal width. If it's less than 0.75, then it's of the class, the first class, the setosa. If it's not, then take a look at petal length. If it's less than 5.05 or 5, then you determine this to be the second class, versicolor, I think. Otherwise, it's virginica. So that's a straightforward decision tree to explain, to communicate. Now, it's making more mistakes than the previous decision trees. So if my goal is to do better prediction, I don't want my research assistant to do this process. I just want to feed new data to the computer to make predictions, then there is no need to simplify the decision tree. I just want it to do a better job in predicting the labels. Another way to create parsimonious model is to do what we call a feature selection. In feature selection is something we looked at. The more feature you add to the model, in general, the better your model is in predicting the labels. But not all features are created equal. This is something we've seen in the previous exercises. For instance, when you looked at the baby weight data, adding one feature such as smoking or non-smoking explains a lot, right? Other features are not as important. The same thing in the cars data set. One feature is such as the country of origin is very important compared to other features, for instance. This is something we can do using a whole range of techniques, generally called feature selection algorithms. We're going just to use a one way in classification trees by using an attribute called feature importance. And this basically ranks the features based on their importance. And you can see that the petal length and the petal width are much more important than the sepal length and the sepal width. And this is something we've seen here, right? Those are the two features that were selected when we constrained the tree to be kind of shallower. So the decision tree algorithm itself, under the hood, ranks the feature based on importance. So we can rely on this information to basically constrain our model. Like I can say, okay, I just want a feature, only one feature in my decision tree. If this is the case, I can select the most important feature, which is petal length, which is what I have done here. Now, if I redo the process again, you can see that my accuracy score did not suffer a lot. But I'm only using one feature now. So now you can see that my decision tree is solely constructed based on the petal length. So this is another way, in addition to setting the hyperparameters, another way to create parsimonious model is to do feature selection. Once again, there is a dedicated number of algorithms for feature selection, and there is a module within the scikit-learn package that does feature selection. This is just an example of using the built-in feature importance attribute in the decision tree. Finally, we're going to take a look at the Titanic example. We're going to create this classification tree to classify passengers who survived compared to passengers who did not survive the Titanic. This is something very important when we do any classification or any machine learning model in scikit-learn. It doesn't tolerate null values. So here is an important decision that one needs to make: how to deal with the null values. Should we drop them? Should we fill them? Should we impute them? And there is no easy answer, because dropping them may create some biases. Because let's say, for instance, there are so many missing data when it came to the deck, and then this create a bias towards probably first or second class passengers, because the decks are well known, or maybe demographics are well known. Or we can fill them, but if we fill them, what's the value to fill them? Or we can impute these variables. So again, this itself is not a straightforward decision, but for the sake of simplicity, I just dropped the null values from this data. What I have done here, I created I selected some features such as the passenger class, the age, whether it's adult male, sibling, passengers, the fare, and whether the passenger is traveling alone. And my target variable is survived. in this case, well, there are two ways I can do it. I can either create, depending on the application, if I want to understand what's going on, I don't need to split my data to training and testing. If I want to predict, I need to split my data to training and testing. In this particular example, there is no reason I split my data to training and testing, since I'm not going to predict. I mean, the Titanic is one-time event, so there is no reason to predict whether the passengers of the Titanic will survive or not, because it's a historical event. The goal of using this model is to understand the dynamics of that event, some of the hidden patterns, what led some passengers to survive and others not to survive. But there is no need to predict that anymore, right? It will not happen again. So that's why I'm not splitting my data to training and testing. I want the model to be used for explanation purposes, and hence I set my hyperparameter to be 3, because I don't want it to have a very complicated tree. I just want to take a look at the tree and understand what's going on. So here we go, and I do that and estimate the decision tree. The accuracy score is now hover around 95%. I can print my tree here. Well, that's the old tree. Hold on. That's the Titanic tree. The accuracy score is 81%, and that's the tree, right? So first, if it's not an adult male, it's a different story. If we have an adult male, if we have, well, actually, if we have an adult male, I'm going actually to use GraphViz here. Export GraphViz, and I'm going to copy paste this to Web GraphViz. It's easier than the text export. Okay, so that's the decision tree. If adult male is less 0.5, it means the person is not an adult male. Then we look at the fare, right? So if it's a low fare here, then the passenger did not survive. That's class 0. If it's a higher fare, then we look at the age again. If, well, the age doesn't seem to matter, so again, this is something that this decision tree can improve on. But if the fare is higher than 10.48, it predicts the passenger to survive. Which basically says that female who paid higher fare tend to have survived, that event. Well, for male, it's a different story. Once we have a passenger who's a male, it really depends on the age. Male with an age more than 43 years did not survive, but a male with an age less than 43, it depended on the fare. Those who paid a fare less than 7.85 did not survive. Those who paid a fare more than that survived. Okay, so that kind of shows some of the dynamics of what's going on. Again, a better understanding needs some, historical background context of what's going on, or what went when the ship sunk. Alright, so that's conclude the discussion of this lecture. We looked at decision trees, and decision trees are very useful for classification. One of their beauties is that they're easier to interpret if we constrain them to be more parsimonious, and they can be used for both prediction and explanation purposes.